Around 1900, all of physics, and particularly Einstein, was in trouble. They couldn't figure out how anything could move. Now, before you complain that I'm exaggerating, check out this cat. You can clearly see that the cat is moving away from Einstein at a constant velocity. But do a little sliding switcheroo, and suddenly it looks like Einstein's the one moving. This is the old-fashioned principle of relativity. But the point is that the switcheroo changes relative things, like position and velocity, and not absolute ones, like the separation of Einstein from his cat. Now for the problem. Before Einstein was even born, physicists showed that the speed of light was one of those absolute things which can't be changed by a switcheroo. So any switcheroo we do has to keep light moving at the same speed. But then it's obvious that we can't do our sliding switcheroo at all, which means we can't explain how anything other than light can move. Okay, I spoke too soon. There is one solution. Do you see it? We were assuming that our switcheroo had to keep every slice of time at the same, well, time. But there's no law of physics that says time is an absolute thing that can't be changed by switcheroos. So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too. Of course, Einstein didn't figure out this special principle of relativity in 1905. It was already done by a guy named Lorentz 10 years earlier. But Lorentz just thought that this time rotation was a mathematical trick. And it took Einstein to step in and, you guessed it, propose that time rotation is real, that time really is relative, and that consequently, simultaneous events relative to one observer aren't simultaneous relative to another. Now that's a real switcheroo of perspective.
According to general relativity, the faster you go, the slower time is in your frame of reference, and the shorter distances seem. At 99% the speed of light, time will seem about 1/7 its normal speed.
There's a famous thought experiment involving a train and a tunnel. The idea is you've got a train and you've got a tunnel which is exactly the same length as the train. And so if you're a train spotter who's standing there beside the railway watching the trains go by, you see this train approaching, and because this train's moving relative to you, you see it Lorentz contracted. It's a bit shorter than it should be. And that means that as it goes into the tunnel, it disappears completely in the tunnel. Right? Because it's shorter than the tunnel, like the tunnel's not moving relative to you, you're standing next to it, so therefore the tunnel is its normal length. But because this train is moving relative to you, it becomes a little bit shorter, so it disappears into the tunnel. Fine, so it actually is briefly kind of hidden at both ends of the tunnel. But now if we think about somebody sitting on the train's perspective, somebody sitting on the train, they think they're stationary, you know, the table there in front of them, they can drink their cup of coffee, when they put it down it just stays there, so they're in their reference frame and everything's normal, and they're seeing the countryside rushing by, and so they see this tunnel approaching them at high speed, and of course because they're seeing this tunnel moving, the tunnel should be contracted. And so from their perspective, they should never completely disappear into the tunnel because they see a tunnel which is shorter than the train, so therefore the train never completely disappears. By the time the back end of the train's disappeared into the tunnel, the front end's come out the other end. Right? And that's all well and good, and okay, maybe they just agree to differ about whether the train is shorter than the tunnel or not. But unfortunately, you can then do another experiment, which is you can say, okay, so if this train spotter actually is, you know, has a lot of power, and bizarrely someone has installed two large guillotines, one at either end of the tunnel, and at the moment the train disappears into the tunnel, he pulls a lever which briefly makes these guillotines come down and then go back up again, then from his perspective that's fine because the train's disappeared into the tunnel. He can do that without doing any damage. Okay, from the point of view of somebody approaching the tunnel, if this happens it's not going to be such good news because from their perspective the train's longer than the tunnel, which means either the front of the train gets chopped off or the back of the train gets chopped off, or both. Okay, and this is something that everyone has to agree on, right? Because if you actually do the experiment, either you end up with a smashed train or you don't. And ultimately that's going to be something that everyone has to agree about. It's not something that you can just say, well, that's just a matter of perspective, that's all just relative, right? Either the train gets broken or it doesn't.
So what happens?
So there is a resolution to this paradox, and the resolution to this paradox turns out to be something very fundamental in relativity, and it's called the relativity of simultaneity, which basically means which things which are simultaneous in one reference frame are not necessarily simultaneous in another reference frame. So in fact, both of these people agree that the train doesn't get smashed, but the reason why they agree the train doesn't get smashed is different, right? The guy who's pulling the lever says, well, the train obviously didn't get smashed because it was shorter than the tunnel, so that was fine. The guy in the train sees something completely different in that what he says is that actually what happened is the train was approaching, before it went right through the tunnel, the front guillotine came down and went back up again. Then after it had pretty much passed through, the back guillotine came down and back up again. And so actually they kind of missed the train as it went through.
In actuality, the total overall speed is slightly less than the two added up. The exact formula is velocity 1 plus velocity 2 over 1 plus velocity 1 times velocity 2 over the speed of light squared. Basically, it's added, but then divided by a value close to 1. Usually, velocity 1 times velocity 2 over the speed of light squared is very small, so the end result is usually close to velocity 1 plus velocity 2.
You probably learned that objects attract each other based on their mass, so you probably grew up thinking that light can't possibly be affected by gravity because light is massless. I know I did. Well, guess what? The source of gravity is not mass. It's energy and momentum, which light certainly has. Of course, regular matter does too. So not only does light get bent passing by a star or planet or black hole, but light attracts the planet or star or black hole in return. To be sure, it's only a very, very small amount, but a small amount is not zero. Anyway, the point is that Newton's law of gravitation is just an approximation. Good enough to get us to the moon, but not perfect. General relativity is better.
But it was first noticed scientifically by Robert Brown, who was a botanist, who saw that if you got pollen molecules and you took the pollen out and sprinkled it on the surface of water and studied it under a microscope, you would see the pollen molecules jittering about on the surface of the liquid, on the water, and he thought that this showed that pollen was alive in some sense, moving all the time, jittering everywhere. So he then tested this idea by putting grains of sand on the surface, or dust, or any other particles he could find, and he found that inert particles, such as a bit of sand ground up, would also jitter around. If I put the grain on the top, it goes in a random motion, a jittery motion, and moves to the side. If I do it again, put it in the middle, I can't get it exactly in the middle, so it's not exactly the same, and now maybe it'll go another way. And it does. And each time you do it, you might get a completely different path.